So this question, I think, is one you're probably all familiar with. I'm not going to elaborate on it at all because I have a lot of material here. Let's get right into it. I'm going to talk about half a dozen strategies. Now, these might not look like funding strategies. These may look to you like smart things to do just from a financial, administrative, and operational standpoint. But I see them as also strategies to actually get a project launched and funded. And this isn't a mutually exclusive list. They're combinations of these things too, as you'll see as I go through these. So let's start with the first one. Whole building energy retrofits. I'll give you an example. This is our cardinal example. At UC Irvine, we've pioneered a whole concept that we call the Smart Lab energy retrofit. We do the same thing in new buildings, new laboratory buildings as well. We've done every laboratory on campus now. All the new buildings built in the last 10 years since we started this program, and every building built in the prior 40 years on the campus. That's all of them. And a lot of people think that what we do is these first two things here. That's basically shorthand for we install the air acuity system, which is a demand-based zone-by-zone system that controls air changes based on real-time sensing of air quality. And so it's a system of sensors and software that does a very good job of that. But that's not all we do. Let's see if I have it. Yeah. We start out by reducing the power density in laboratories, just the lighting, because we're trying to reduce air changes. That would be the limiting factor if we didn't do it. So that's synergistic with the first two items. These things result in less air flowing through the building, so we want to optimize the exhaust fan discharge velocity without using bypass air. Bypass air is a big waste of money as far as and energy. So that's related to this. So you can see these things are all integrated. It's by doing an integrated, oh, and this final one, sorry, I didn't mean to pass over this one. We put in what we call an information layer, which is pretty rich. It actually, for our whole campus, not just laboratory buildings, but primarily the laboratory buildings comprise 465,000 data points being measured every 5 seconds. It's happening right now as I speak. Every 5 seconds we're measuring 465,000 data points. And so that's necessary when you make your building smart enough, as we have, that you need this kind of information layer to keep a smart system smart. What this does, when you do these things all together as a synergistic, optimized collection, a whole building retrofit, or a whole building design concept in the case of a new building, on our retrofit projects, we've achieved 61% energy reduction. 61%. Way more than we ever thought was possible. It's because of the synergies of having a whole building retrofit concept. Assign dollar values to everything you can, and try to clarify the things you can't assign dollar values to. So let's talk about examples. This is a typical energy retrofit project of about 10 years ago. So this isn't a whole building retrofit. This was actually before we started doing whole building retrofits. So this was a case of a building that had on the roof a whole bunch of individual exhaust fans, one for each fume hood actually. And they were belt driven. They were 1 and 2 horsepower motors. There was just like a whole farm of old 50-year-old fans up there. So the way we look at justifying a project is, there's a pretty good incentive in California. We subtract that right off the top. Then we end up with a number, and we figure out what that would cost us in annual debt service. We finance about $75 million so far in energy efficiency projects at UC Irvine using 15-year revenue bonds. And so we want the bottom line here to say that the debt coverage ratio is 1.15 or greater, meaning that in year one we want the savings, the dollar value of the savings, to be 15% greater than the debt service. That's our margin of safety, financial margin. So when you add in, though, a number of additional benefits, and we didn't know we'd have all these additional benefits initially with this project. We started realizing these in our program as we kept rolling it out year after year and getting deeper and deeper into energy efficiency, and we realized the co-benefits were pretty important. Now this is a list that doesn't apply to every project. Some of these things apply more to lighting projects, like reduced HVAC for more efficient lighting. And some of these things are like extended service life of equipment that turns or is hot, like air handlers and motors. And down at the bottom you do see a cost of carbon. There is actually a cost of carbon in California. So that's one of the costs, savings actually, avoided carbon costs. So when you look at this project, this is actual numbers. This project, using today's cost of energy, would have just been 1.15 debt coverage, right on the borderline of not doing it. And if we had projects that had a better debt coverage ratio, we would have put this on the back burner and not done it. It turns out that some of these numbers have changed since then, but let me show you what happens when you go now to the next step here. These are the co-benefits. A lot of deferred maintenance. Some of these other things, I won't read these for you. Avoided carbon costs at the bottom. So what does this do for the project? This is what it does. The annual debt service went down because I subtracted out the $70,000 that really is deferred maintenance. So we don't have to count that in justifying this as an energy project. This went up because of these factors that we're able to monetize and add into the benefits. And also we went with the marginal cost of energy because we realized we've been making a mistake all the time. We've been using the average cost of energy to figure out what the debt coverage ratio was or the payback, whichever way you want to look at it, on an energy project. What you're reducing with an energy efficiency project is the last megawatt hour you're going to buy. And so it ought to be priced at what the last megawatt hour costs at the margin. This is a big difference. I think that's probably $5,000 of the additional savings here. So that's an example. Expanding this idea to take a life cycle perspective is even more interesting. So this goes back to that Smart Lab project I started out with. And this is, I'm going to combine the average of all the retrofit projects we did. Some of these things add costs and some are benefits that reduce costs. So this is obviously the cost of the project. This is a subtraction. This is a big subtraction. This is a cost we added. We added a safety specialist with all the energy savings because we were changing air changes zone by zone throughout every lab building. So we have a person now on staff who just optimizes air changes zone by zone because frankly there are a few airborne hazards which are not sensed by the air QD system. So we have a better inventory of what's going on lab by lab. And this was easy to pay for because these savings were so high. So we actually paid for it out of energy savings. Also there's some additional costs in here for the maintenance of these increased controls. The 465,000 data points I mentioned, that cost is spread across a number of projects. There is an impact. And these other things are savings. So let's see. Oh, and before I show you the numbers, let me show you the assumptions, just because I want to be really clear about this. This is all the data I'm going to show you now are 2017 dollars. In other words, we didn't inflate them and then discount them. None of that mumbo jumbo. It's all 2017 constant dollars. There's about a plus or minus 20% factor because this summarizes 13 projects that provide the basis. It's all projects which had VAV and DDC to begin with. The projects that were older, that didn't, we had a couple of constant volume buildings and a couple of dual duct buildings. They cost more, but they also save more, so that they would be analyzed separately from this model. Carbon costs are the current California emissions allowance price. And this is, look at this. I want you to see this because a lot of people think that the reason we've gotten these kinds of savings at UC Irvine is because they assume that our energy costs are north of 15 cents per kilowatt hour. No, this is what it is. It's co-generated electricity. And when we started this program, it was 8 cents per kilowatt hour because natural gas was a little bit higher 10 years ago. So it's not based on 15 cent per kilowatt hour costs. So here, these are the 50-year total costs and total benefits for a smart lab retrofit of a typical laboratory building. In other words, one of the 13 that I averaged to do this model. So the 50-year costs in 2017 dollars are $32 per gross square foot. The benefits, more than, what's roughly 3 times that much. This is a no-brainer. When you look at it in life cycle terms and throw in all the costs and all the benefits, it's a no-brainer. Now the problem is, do you have the capital to finance this? And we do have the capital because we don't have a debt capacity issue, because the whole campus, as an intentional financial strategy, in 2001 decided we would double our housing supply using third-party housing. So American Campus Communities has built 6,000 plus bed spaces of third-party housing, and that's not on our balance sheet and it's not on our debt capacity. So that's why we've been able to finance these things with revenue bonds. Let's see. Another strategy. Well, this is kind of obvious, but let me just show you an example. This is a health sciences research building. This is one module of a building that goes this way and this way. It has, so this is module C in a building that goes A through F, I think. We thought of tearing this down. It's kind of an old dog, but it had pretty good bones. And facilities people know what I mean by that. The structure was good. Seismically, it's good, which is important in California. The mechanical systems were shot, though. I'll give you some examples. Yes, you're looking at rusted through air handlers on the roof. It was that bad. You can see here some leaky roof and some areas that are obviously low points. It's not well drained. It was not. We went through a design build competition process. This was what you see in the base bid. We set aside some money for alternates. We didn't know how much of this would make it into the base bid because we use a highly incentivized design build competition process where we incentivize the more they can put into the base bid. We didn't have to put very much into the alternates, so this is the full scope of the project. So you can see there's a lot of HVAC stuff up here. There is some finishes and improved appearance. T-bar ceilings were added in here, and practically everything in the mechanical room was replaced. 40-year-old building, so it needed that. Before, after. This system, this air handling system, the energy savings, 80%. That's kind of a phenomenal number. The reason you get a number like that is when you start with air handlers that are actually rusted through on the roof. So that's why. Yeah. Interior supply ductwork before. Exhaust ductwork, yes, that is transite. Yes, it is gone now. Now you can't see the ductwork because of the ceiling. Adding the drop ceiling is actually an energy saving feature because remember, we're looking at air changes, and so when you reduce the volume that was above that ceiling, you get away with less air changes in the building. That's also one of the reasons we got a number as high as 80% savings. Oh, by the way, in the lab block here, the energy use intensity is 36 now. Unheard of number. And it does have the full Smart Lab ensemble, including Air Acuity in it. Lead off with projects to provide, you can read this. What I mean here is, well, I'll give you an example. We're improving lighting. We're removing fluorescent lights and putting in high-CRI lighting, color rendering index of 90 or above, across campus. And in some places it's hard to make that thing work because we've already retrofitted our lights down to 25 watts with a ballast factor of 0.71. So they're pulling about 20 watts now. So you can see the numbers don't quite work out. But when you talk to the visual artists, yeah, they want better quality of light. They're dying to get rid of fluorescence. And these people are even more interested. These are the clinicians. I won't go through this whole list, but we started with dermatology because we found out that dermatologists need to be able to see very subtle differentiations in red skin tones of skin diseases and skin conditions. And it's not just dermatologists. It's, well, I'll give you another example. In the neonatal ICU, my sister is a pediatric nurse. How do you tell the health of a baby? By how red their skin is. And that's, you know, they're getting good oxygenation if their skin has a good, healthy red tone. And that's true of all these other areas where, see, with the fluorescent light, the reason they have such a low color rendering index is because they have almost no content in the red part of the spectrum. That's why they're down in the low 70s in terms of color rendering index. These people, even if this project doesn't even break even, we're going to do this project because these people want it for their patients and they want it for their diagnostics. So this one is a big one. It's actually bigger than we thought. It turns out that this cogeneration plant now, because of all the Smart Lab projects that we did, is way too big. We actually have an oversized cogen plant. we'll eventually need that because we're still a growing campus. We'll grow into this capacity. We have excess chiller capacity. We have 14,000 tons here and 2,000 tons over here. And this is all part of that same infrastructure. Everything you see on this chart is oversized now and has capacity waiting for the campus to grow because of energy efficiency. If we'd had to add chillers and cogen in order to grow, that would have been a big factor, a big cost factor. So this is a huge number, and you saw it when I gave you those examples. Mistakes to avoid: don't set the bar too low. Don't start compromising with your financial officer. I can say this to you because I was the person who approved these projects for 40 years. So I've seen this from the application side, I've seen it from the approval side, I've seen it from the UC system level, because we're looking at the whole UC system and trying to figure out why some campuses are going much faster than others at pursuing deep energy efficiency. Oops, sorry, pushed the wrong thing. Don't waste low-hanging fruit, especially if you have an opportunity to combine things that have a fast payback with things that have a longer payback. I mean, our lab project was a good example. In the smart labs, the lighting paid off in a few years. The air acuity and smart controls and what I call the information layer probably has an 8 or 9 year payback. Combine it, you actually have a project which, well, you saw the numbers, they look good. So don't waste that opportunity. And these last two, these are really two sides of the same coin. If you haven't done some of this deep energy efficiency of the kind I'm praising in this presentation, make it an advantage to be late to the party. It actually is an advantage because what we did here is a lot of, we were the early adopters on some of this stuff. And there are other campuses that have done that too. Find a campus that you want to copy and just take a page out of their book. We're all going to share it because we all believe that reducing carbon footprint is very important. So you can take that and turn it to advantage. I'll be around. I realize I've covered a lot of details. I'll stick around as long as necessary to answer any questions. And if anybody wants a full slide deck without even downloading it, I brought 10 zip drives over there, and the first 10 people that want them can get them. Thank you.